So at the end of last class, we were discussing the normal distribution. And I had mentioned that the normal distribution is used a lot in finance to characterize the probability distribution of rates of return. And once we start working with data, so essentially the week after next, we'll see why the normal distribution is used a lot, because it matches what we observe in the data, pretty well. But I went through an example to highlight some problems with taking the normal distribution on faith as a good distribution to characterize a rate of return. And so I want to go through this example again and to reiterate the points that I made last time. So we're going to discuss why the normal distribution may not be appropriate for simple returns. So again, we're looking at a simple return, which is just a percentage change in price over some period of time. So let's consider, say we have an annual investment. So we're going to buy Microsoft today, and we're going to sell it 1 year from now. And RT is going to represent the annual rate of return on that investment. So let's just assume that the annual rate of return follows a normal distribution, and the mean of this distribution is 5%, and the standard deviation is 50%. Okay? And so if we think of anytime you have a problem where you write down a distribution, it's worthwhile to draw it. So I'm telling you I have a normal distribution. We have a normal distribution. It has a bell-shaped curve. And here, my rate of return is normal with mean 5% and standard deviation 50%. Okay? So we know the center of this distribution is at 0.05. And the standard deviation, gives us a spread about the average. We go out plus or minus 1 standard deviation, we get 67% of the area. We go out plus or minus 2 standard deviations, we get 95% of the area. You go out plus or minus 3 standard deviations, you get 99% of the area. Okay? So if we think of this rate of return, so the mean plus a standard deviation, so if this is mu of r, we can go mu r plus sigma r, and then we can go down mu r minus sigma r. And this would be 0.05 plus 0.50, and this would be 0.05 minus 0.50. So if you go mean plus a standard deviation, you're out at 55%. You go to mean minus a standard deviation, you're down to minus 45%. So notice that in this example, going out 1 standard deviation below the mean, you're losing 45% of your money. So that's almost half your money you've lost. Now, if you go out 2 standard deviations, you're down 5% minus 100%. And so you're down 95% of your money. If you go out 3 standard deviations, you're down more than 100%, right? So you've lost more than your initial investment. Well, that can't happen, right? So the problem is that the normal distribution is defined for all real values. It's defined for returns between minus infinity and infinity. And we know that a rate of return, the smallest value it can be is minus 100%. So we know the return has to be bigger than minus 100%. And based on this distribution, we can calculate what is the likelihood that we can actually lose more than our initial investment. And so what's the probability that the return is less than minus 1? Okay? So you're in the far left tail of the distribution. And if you use the norm dis function in Excel, for example, we find that there's a 1.8% chance that with this normal distribution, you can lose more than 100% of your money. Okay? And so that doesn't make any sense at all. And another way of viewing this is that this distribution implies there's a 1.8% chance that the price in the future is less than 0. Okay? So again, that doesn't make any sense either. So this is an example to illustrate why a particular normal distribution may not be appropriate for simple rates of return, because it could imply negative prices. Now, what can we do about this? Well, it turns out that if we consider continuously compounded rates of return, and again, the continuously compounded rate of return is the logarithm of 1 plus the simple rate of return, right? And given the continuously compounded return, we can solve back for the simple return by taking e to the continuously compounded return minus 1. Okay? Now, instead of assuming a normal distribution for the simple rate of return, we can assume a normal distribution for the continuously compounded rate of return. Okay? So let's take this same distribution. The continuously compounded return has mean 5% and standard deviation 50%. Now, the thing that's a bit counterintuitive about continuously compounded returns is that it's perfectly okay for the continuously compounded return to be smaller than minus 1. For example, suppose the continuously compounded return is minus 2. So we're saying the continuously compounded return is minus 200%. Does that make sense? Well, what is the simple return that's implied by this continuously compounded return? It's e to the minus 2 minus 1. Well, that's minus 86.5%. So if the continuously compounded return is minus 200%, you've actually only lost 86% of your money. Okay? So, and in fact, the continuously compounded return is defined for any value between minus infinity and infinity. Right? Suppose the continuously compounded return is minus infinity. Right? What is the implied simple return in that case? Minus 1, right? Because you're going to get e to the minus infinity, which is 0, minus 1, so it's minus 1. So if the continuously compounded return is minus infinity, you've lost all of your money. Okay? So the continuously compounded return is perfectly sensible from minus infinity to infinity, and so the normal distribution is perfectly okay to describe the distribution of the continuously compounded return. And so, for example, you know, the probability that the continuously compounded return is less than minus 2 is the same that the probability that the simple return is less than minus 86.5%, and you know, there's a very, very small chance that will happen. So this is an example why we like continuously compounded returns, because we can use a normal distribution. We don't run into any of these problems that, you know, we have returns could be, you know, less than minus 1, or prices could be negative, or things like that. So again, I want to emphasize that this is another reason why throughout this course we will often do probability modeling with the continuously compounded return instead of the simple return. All right. Now, the previous two examples give rise to the following log normal distribution. So, for example, if we start with a random variable that's normally distributed, for example, if the continuously compounded return is normally distributed, and we define a new random variable that's the exponential of the first one, so remember, so 1 plus the simple rate of return is e to the continuously compounded return, it turns out that y, which is the exponential of x, has what's called a log normal distribution. Okay? And the log normal distribution has parameters mu x and sigma x squared, and these two parameters are exactly the same as the parameters of the underlying normal distribution. Okay? Now, the mean of the continuous of y, which is the exponential of x, is not mu of x. And in fact, it takes a bit of work, but you can show that the mean of y is equal to the exponential of the mean of x, right? Because y is the exponential of x. You might think that the mean of y would be the exponential of the mean of x, but it's the exponential of the mean of x plus the variance of x divided by 2. Okay, so there's a slight adjustment. And this adjustment comes from the change of variable formula in calculus and so on. So we can deduce the mean of y as the exponential of the mean of x plus sigma squared divided by 2. And then more tedious calculations can be done to show that the variance of y, or sigma y squared, is the exponential of 2 times the mean of x plus the variance of x squared times the exponential of the variance of x minus 1. So it's a pretty complicated formula. So let's look a little bit at the relationship between the normal distribution and the log normal distribution in the context of returns. So we'll start with the assumption that the continuously compounded return follows a normal distribution with mean 5% and standard deviation 50%. Now, we know that the 1 plus the simple return is equal to e to the RT, right? So we can think that in this relationship here, x is r and y is 1 plus r. So 1 plus the simple rate of return, which is e to the continuously compounded return, will follow a log normal distribution. And the parameters of this log normal distribution are the same as these things up here. But the mean of 1 plus the simple rate of return is the exponential of the mean of the continuously compounded return plus 1/2 the variance of the continuously compounded return. This turns out to be 1.191. Notice that this is the mean of the distribution of 1 plus r. So the mean of the distribution of r would be 1.91 minus 1. So this is saying that the simple rate of return would have a mean of 19%, whereas the mean of the continuously compounded return has a mean of 5%. So notice that the log normal distribution kind of pushes out the mean a bit for the simple return. And then we can deduce the variance of 1 plus the simple rate of return by evaluating this horrible formula. We get something that's 0.563, and so again that's different from the variance formula that we have. The variance for the continuously compounded return is 0.5 squared. So here I'm graphing the two distributions. So this is the distribution for the continuously compounded return, and so we can see that its mean is around 5% here, and it has a big standard deviation. And the blue line is the distribution for the this would be for 1 plus the rate of return. And so notice that this thing starts at 0 because when r is minus 1, 1 plus r is 0. So the gross return starts at 0. And we see that it has a shape that is a little bit asymmetric. So the log normal distribution, because when you take e to the x, you always have something that's positive, that produces a bit of skewness or asymmetry in the distribution relative to the normal distribution. So we see this log normal distribution has a bit of a long, right tail, and so this is referred to as positive skewness, and we'll see that later on. So again, this is an example where you start with a normal distribution for a variable, you make a transformation of that, and then we can deduce a distribution for a transformation of that variable, and then we can work with that. Okay. Now, if you're working in R, so one of the nice things about R is that it has functions for essentially any distribution you can possibly think of. So if you want to do computations with a log normal distribution, there are 4 functions: R, L norm. So L norm stands for log normal. And this allows you to simulate data from the log normal. You can compute the cumulative distribution function with PL norm. You can compute quantiles with QL norm. And you can compute the height of the curve. So when I plotted the graph, I used the DL norm function. And so, again, so anything you want to do with the log normal, there's an R function to do this. Now in Excel, there are some functions. You can compute the CDF of the log normal, but you can't simulate random variables, and you can't compute quantiles, and you can't compute the density. So Excel only has some functions for dealing with a log normal, but not a full array. And again, this is a reason why we're using R for the statistical stuff, is that it has a lot more things built in, whereas Excel does not.